Welcome to Lesson 8b, Introduction to Induced Drag. In this lesson we compare drag forces on infinite span, or 2D airfoils, and finite span, or 3D airfoils. We'll define induced drag and trailing vortices, and we'll discuss some other features of finite span wings, such as upwash, downwash, and the starting vortex. By introduction, let's consider a 2D circular cylinder with circulation, as discussed in a previous lesson. When you generate a potential flow by superposing a free stream and a doublet, you get flow over a circular cylinder of radius A. When you add a circulation of gamma A, we generate lift. It turns out that the drag is 0, but the lift is rho times u times gamma A. And recall that these are both per unit depth into the page, since this cylinder is two-dimensional or infinite in span. It turns out that for any two-dimensional closed body in potential flow, the drag is still 0 and the lift is still rho u gamma A, where again these are per unit depth into the page. Since it applies to any closed body, it applies to airfoils as well. So if we have some airfoil in a free stream and we add the appropriate amount of aerodynamic circulation gamma A, we'll generate a lift force. And for this airfoil, drag is 0 and lift is rho u gamma A. I say the appropriate gamma A because we must satisfy what we call the Kutta condition at the trailing edge, namely that the streamlines must flow smoothly over the trailing edge. We'll talk about the Kutta condition in more detail later. For now, let's just suppose we satisfy the Kutta condition in all the examples we do. This is for a 2D case, namely an airfoil of infinite span. What about the 3D case, or a finite span airfoil? It turns out in this case that the drag is not equal to 0 when the lift is not equal to 0. In other words, there's a drag that depends on the lift. This drag is called induced drag because it's induced by the lift. Let's consider the simplest case of a chopped off wing. In other words, it's two-dimensional with the same airfoil shape, angle of attack, etc. But it's just sliced off at the ends, or the tips. We'll let S be the span, and we'll let C be the chord. And I'm trying to draw this three-dimensionally. The wing will be at some angle of attack in a free stream flow. If we take a little slice of this wing of dimension dy into the page, where Z is up and Y is the dimension along the span, and we let dy be a little slice through this wing, we can look at this slice in a little more detail. It turns out that the streamlines, if we have the correct gamma A, will flow smoothly over the trailing edge, and a lift will be generated because of the circulation as we discussed. We can approximate the lift L on our little slice as the two-dimensional lift per unit depth times the thickness or span of our little slice dy. And more properly, I'll call this dl, since this is a little slice and now we'll integrate. The total lift is found by integration, where if we set the origin in the middle of the airfoil, we integrate from y equal negative s over 2 to s over 2 of dl, which is rho u gamma a dy. And we approximate for gamma a equal constant and rho u equal constant that L is approximately rho u gamma a times this integral dy, which is simply S, the span. This is approximate because of the end effects. This analysis works well for a slice somewhere near the middle of the span, but when we get close to the tips, this equation no longer holds. But this is a pretty good approximation, especially if S is large. Note also that here L is the actual lift, not lift per unit depth. And it turns out, as we mentioned already, that the drag is not 0. This is what we call induced drag. Why is there induced drag? Well, again, let's sketch our wing, which has circulation gamma A in free stream U. Now imagine taking a cylindrical surface encompassing the entire wing, and think about this as a vortex tube. We go back to a previous lesson and recall the Helmholtz theorem, number 3, which states that a vortex tube cannot end within the fluid. In other words, this vortex tube, which has a net circulation gamma A, can't just suddenly become zero circulation at the wingtips. So what happens to this circulation as we hit the end of the wing? Well, because of Helmholtz, it has to somehow turn in both tips and head into the wake. I'll redraw this for clarity. If this is aerodynamic circulation gamma A through the wing, the vortex turns so that it doesn't end in the fluid, and the total circulation must remain gamma A on both sides. These vortices are called trailing vortices or tip vortices, and we see them behind airplanes as what we call contrails. By the way, the reason I used a vortex tube instead of just a singular vortex here is that the circulation can be distributed along the airfoil body surface, but the net circulation around the entire wing is gamma A. This is just a simple model of that, where all the vorticity is concentrated in one vortex. Well, these vortices can't just end in the flow either, again by Helmholtz's third theorem. So what happens to them?
Does it have something to do with vortices left over at the airport?
That's right, Ned. Eventually they end up back at the airport in what's called a starting vortex. It still has circulation gamma A, but notice that it's opposite sign to that on the wing. Thus Helmholtz is satisfied by this closed vortex. The starting vortex is generated when the wing increases its angle of attack and generates lift, and leaves behind the starting vortex at the airport. Note that these two vortices that are parallel to each other and opposite sign are mutually self-inducing, causing these trailing vortices to move down as the airplane moves to the left in this case. The flow in the middle is actually going down as well due to these vortices, and we call that downwash. On the other side of the vortices, we have upwash. By the way, these contrails are visible behind aircraft because of condensation of water vapor in the air in the vortex cores. In other words, in the middle of these trailing vortices where the pressure is low, which also leads to low temperature in the cores, which is what leads to condensation.
I always thought contrails were smoke from the engines.
No, Ned, they're not. They're not smoke. They're water droplets, kind of like clouds. Here are several examples of contrails formed by the tip vortices. There are always two contrails because of the trailing vortices. Even when there's four engines, as in this case, there's some smoke and other effects mixed in here, but eventually they merge into two trailing vortices or contrails. Here's another example that looks kind of cool. Here's my sketch of the trailing vortices that I created a little more nicely on the computer. And here's a picture of streak lines where you can see the trailing vortices or tip vortices being generated at the tips of this airfoil. As I mentioned, the circulation over the airfoil is sometimes distributed and not all concentrated in one vortex. But the net circulation around all of these vortices is what we're calling gamma A. Notice how the streak lines move in a helical pattern because of the vortices. Here's another cool picture of a large tip vortex visualized by red smoke. And here we see both trailing vortices visualized by clouds. Tip vortices also occur in propellers, wind turbines, and other rotating turbomachines. In this classic picture from the Garfield Thomas Water Tunnel here at Penn State, we visualize these tip vortices because of cavitation. The pressure here is so low that the water cavitates, and you see this cool spiral shape due to the multiple blades. Fighter jets often fly in a V formation like this, where they take advantage of the upwash and downwash of the other aircraft near them. They learned this trick from geese. When one goose flies outward from the one in front of it, it gets a benefit from the upwash at the wingtip, giving it some free lift due to the upwash. Here's another picture of geese in a V formation.
Dude, do you know why one side of the V is always longer than the other?
No, why?
Because there's more geese on that side.
I should have seen that one coming. Here's one of my favorite Far Side comics. These guys say, look what they're doing. I want to quickly show an alternate way of thinking about the generation of tip vortices. Namely, if we look at the airplane wing from the rear, we know that since there's a lift, the pressure must be higher on the bottom of the wing than on the top of the wing. That's why people in turbomachinery or aeronautics call this the pressure side and this the suction side. Well, we know that fluid naturally flows from high to low pressure. Thus, there's a tendency of fluid to flow from the high pressure side to the low pressure side on each tip of the wing. Redrawing this without all the pressure forces, we see why there's a downwash in the wake of the wing and there's an upwash on either side of the wing. And you can visualize why the tip vortices form. Again, in a three-dimensional view of this, the upwash and downwash lead to the tip vortices or the trailing vortices. What does all this have to do with induced drag? It turns out that these tip vortices are the reason or cause of induced drag. The tip vortices are formed because of the lift, as we discussed, and the lift induces drag, which we call induced drag. In the next lessons, we'll examine how these tip vortices generate induced drag. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.